I'm pleased to introduce our next speaker, who is the professor of atmospheric chemistry at Harvard. I'm sure you all know, a member of the American Academy. He's a great friend and advisor to the foundation. Very pleased to have him talk to us today about the teaching aspect of chemistry and this program, which is an important part of this whole program. So welcome Jim Anderson. Thank you.
Thank you, Scott. I should start out by reiterating the respect I have for the mission of the Dreyfus Foundation to advance societal objectives through the application of the chemical sciences and engineering. And it's remarkable the foresight that went into this mission statement, because now more than ever that's certainly true. I should also give a little bit of background on what I'm going to say, and I'd like to come back to what President Decatur said this morning, that some 17,000 students are engaged in undergraduate education in this country, and they have 2 plus or minus parents. So that means that some 35,000 parents are involved, because of course they ask their son or daughter when they get back, well, what did you learn this term? In parentheses for my $40,000. And the answer that comes back from that is a very important thing to contemplate. And that's part of what I'm going to talk about today. The other thing is that a prejudice I have that was part of the instigation for this was that I was a physics concentrator at the University of Washington in the 1960s, and we started out with 300 physics concentrators, and 19 of us finished. And at that point in time, I thought, well, I'm a little proud of myself for that. But as time went on, I realized that vastly more creative talent was eliminated from those 300 students than was ever kept in the final 19. And also, this was the height of the Cold War, so the context that was driving my interest at the time was the Cold War. And if you weren't in physics, you couldn't contribute to a solution to the Cold War. So going into space physics was a very important thing, and I ended up at the Joint Institute for Laboratory Astrophysics, and I learned molecular spectroscopy from a young professor by the name of Dick Zare, who taught me Hertzberg. And then Herb Broida taught me about discharges, which led to my fascination with free radical kinetics. So all of these factors in the passage of time played in on what I'm going to talk about today. And the issue is that the rapid development of research has infused science and technology, of course, into the core of science. We heard a lot about that this morning. And the question is that true of the time rate of change of university curricula? And it certainly is at the junior-senior level, and it certainly is at the graduate level. But the issue about the infusion of science and technology into society actually comes back in a very profound way to the earlier years, and how do we develop an innovative university-level curriculum that brings a proactive engagement of science and technology into the nation's future, which is to say, into the future of the students that we have. That's the question that's on the table. And certainly it's a central responsibility of universities to look forward in time and say, well, when one of our students walks out with their diploma on the morning of commencement, what are they actually confronting? What is it that's necessary that they know in order to be a proactive member of society? So now we're cutting off a little bit. Is this possible to fix? Anyway, so university graduates today are facing the question of what technical forces are shaping the modern world. but also where are the frontiers of innovation and what are the implications of those advancements in the professional endeavor, but not just in the sciences, also in technology, international economics, government ethics, journalism, law, and education. And this, of course, is now profoundly affected by the problems that we confront on global energy and the ramifications of very rapid climate change. And I'd like to talk about climate change and energy technology today, but I was not allowed to. All right, finally, which public policy strategies are founded on sound scientific technology and which ones are not? So this is something that, of course, all members of a voting society need to understand. So there's a rapidly growing compendium of research that's shown that college graduates across this country, let's see, 6,000, 5,000 a year that graduate, are really very ill prepared to know the fundamental substance behind many of the issues that are confronting us today. And the research has shown that a significant contributor to this is that the scientific foundation that occurs in the first year of physics and chemistry is essentially to blame for this, and particularly courses that are taught as isolated material without a larger compelling context send a message that's exclusive rather than inclusive. And by that I mean, you know, if I'm sitting next to Dick in a freshman class, he's working a quantum mechanics problem faster than I am. If the issue is the relationship between what's taught in that class and my perception of elimination, which is to say there's one axis in this, and that's scientific talent, I'm going to look at Dick and say, well, you know, he's going to be the great scientist, I might as well do Irish poetry. But if it's inclusive, and it places those ideas in a larger global context, then I'm going to think, well, Dick may be the great scientist, but you know, I can argue a case in front of the Supreme Court, perhaps better than he can. I can have a startup company that converts sunlight to hydrogen and change the lives of 4 billion people. But one thing I know for sure is that if I don't understand these fundamental principles of thermodynamics, electrochemistry, quantum mechanics, and so on, I can't take a proactive role in the unfolding society that infuses this technology and science into the public fabric. So this large attrition from the physical sciences is something that's endemic, and some universities are much better at this than others, but the idea is that we're going to eliminate students in the freshman year because we want to find the right stuff for graduate school. And of course, one of the great ironies is that these course structures are based on hourly exams, and they place a huge emphasis on a horse race to complete those exams as quickly as possible. And they don't actually sort out, discover, and elucidate the talent that's actually required to contribute both to society and to science. And I'm going to mention the life sciences, which is the antithesis of this, but in the physical sciences, there's a tendency to say, well, we gave you the atomic bomb, NMR, radar, so on, and you owe us research support in perpetuity. And by the way, we can flunk your kids out of freshman chemistry and physics with impunity. And this is an endemic problem. Life sciences, of course, are the reverse. They took biology, molecular structure, blended them in a profoundly innovative way, and we've heard about a lot of this morning, and they took societal responsibility. So we're going to address cancer, HIV, world disease, and the life sciences haven't been the same since. All right, so what's the dynamic of higher education in the physical sciences today? Well, this is a typical plot. On the ordinate, we have freshman, sophomore, junior, senior year. At Harvard, we have about 65% of students coming in interested in science, but the attrition after the first year or two is remarkable. And this is a particularly endemic problem nationally. And so this creates this zone of scientific and technical illiteracy that really starts in the freshman year, and addressing this problem in the freshman year is the single most important way to go after the problem. And these public policy debates that go on, there's essential information that's necessary to engage in that debate. And also, what about the foundation of information to know enough to know how to vote? And of course, all of this was true even a year and a half ago. Okay, so our university curricula keeping up with the rapid changes globally? Our university curricular structures designed to keep up with a rapidly changing world? And certainly they are in the upper levels and in graduate school. They define it. So our university is providing the broad spectrum of graduates with this information they need. And how many of you have heard Joe Handelsman discuss this? She was a Hirschbach lecturer about 3 years ago at Harvard, and the centerpiece of her discussion was when she was at the University of Wisconsin. Sorry, Randy, you have to see these. She has about 200 videos of asking juniors and seniors and graduating seniors fundamental questions, such as why are there seasons? And only about 25% knew the answer to that. A number of them said, well, the earth is closer to the sun in the summer. Where do the leaves come from on the trees? And a vast fraction had no idea. Another quarter or so said, well, all this material goes up through the trunk and it creates somehow. These videos are shocking, and she also went to the state capitol and asked legislators the same manifold of questions. You really should have her give a talk because it's profoundly eye-opening. And by the way, I think many of you know that Jay Leno actually started this at Harvard commencement about 15 years ago. He stood outside and asked Harvard students the same kind of questions. The performance wasn't any better, but it's an incredibly interesting thing to look at, observe, and see what her results were. So rather than having this attrition from the freshman year on, what's necessary is to have an inclusive course structure so that students are drawn into this. So as they move from their freshman, sophomore, junior, senior, they're actually putting all of these crucial pieces to be a proactive member of society together as time progresses. Now, Carl Wyman, of course, came at this from a completely orthogonal point of view. He did research on how students actually learn freshman chemistry and physics. And he said there's solid evidence that shows that this failure of formalism first, where the isolated ideas are presented as a formalism, and this is what he calls disembodied knowledge. And what he found was that students can't attach this knowledge to any context. And when they can't attach it to a compelling problem, they don't retain it. And more than that, it goes into a part of the architecture of the human brain that has a great deal of difficulty extracting that information for important applications to problems. It is isolated when it goes in, and it's isolated from that point forward. He's given a number. In fact, he gave another talk at Harvard just 4 weeks ago, and it's really important to listen to. Then E.O. Wilson, that we all know, has said, if I learned anything in my 40 years of teaching, it's the best way to transmit knowledge and stimulate thought is to teach from the top down. Begin by posing large problems, questions, and concepts of the highest significance, and then peel off the layers of causality as they're currently understood. And this couldn't be more important. So we need a new strategy for introductory chemistry. The physical sciences whole is key to solving problems of immense concern. Central role and responsibility of the physical sciences in society, as the life sciences have taken. Universities have the primary responsibility to prepare graduates. large exodus of undergraduates from the physical sciences. Introductory courses taught without a compelling context are exclusive rather than inclusive. All this research that's been done and this illiteracy of university graduates that Joe Handelsman has pointed out. So that led then to the combination of considerations that drove the creation of this course I'm going to talk about, which is called Physical Sciences 11 at Harvard. And the title is Foundations of Frontiers. That is, it looks at the cutting edge of research, but it also engages in building a very in-depth foundation. This is actually the honors course at Harvard. And the depth of thermodynamics, electrochemistry, quantum mechanics, bonding, kinetics, nuclear, it's far more difficult than freshman courses have been over history at my university. But it does outdraw the easier course by a factor of 2 to 1, 3 to 1, somewhere in that range. So the students are opting to take a much harder course. And of course, that leaves us with a remarkable student body to work with. In fact, Katie Walter, that many of you know, was one of the very early students in this course design. And I'll never forget, I was sitting in my office, and Katie comes in, steam pouring out of both ears. She just talked to Drew Faust about the collision between climate and energy and went into all of the details. And our president at the time looked at Katie and said, "This is very compelling. I think I'm going to buy a Prius." And Katie just went right through the stratosphere. She was so upset. She came straight over to my office, and I said, this girl is going a long distance soon. Anyway, so how is Physical Sciences 11 designed? Well, a part of it, of course, is frontiers and foundations, but the other is a molecular and global perspective, and that is if you track the way in which molecular level processes map into the global structure, it's remarkable how much control the global scale has exerted upon it by the molecular scale. So that's an important part of developing this linkage. And then the recognition of the fact that developments at the union of chemistry and physics are really key to solving an array of rapidly emerging global scale challenges provides the context. And so context is the tugboat that draws students through far more difficult material, because if they see, as you're presenting it, why it's so important for solving those problems, it's a huge impetus. And so that's this global context that's intrinsic to the course structure. So what does that mean? Well, it means that if we look at innovative new materials, nanostructures, self-assembly, in this context, along with human health, molecular cellular imaging, low-cost disease detection, energy production, storage, distribution, feedbacks in the climate structure, technology and electronics, electric automobiles, that context can be coupled to these core ideas in thermodynamics, quantum mechanics, kinetics, nuclear, and so on, by the use of case studies. And so the idea then is that we have all of these contextual issues on this vertical axis, and the central ideas of thermodynamics, quantum mechanics, and so on. And the idea is to weave these together as the course unfolds. And you know, I tell the students that they're going to be in the 99th percentile when they finish the course, and they don't believe me, but actually examination has turned out to be true. In the union of these contextual issues and the fundamentals, we have many, many people who understand this axis and that axis, but it's the connection between those two that's the potent contributor in this case. So the textbook, so this is the textbook, and when Katie Walter took the course, I was just coming to the conclusion that this course had to have a textbook, because 4 or 5 independent sources, it doesn't work well with freshmen. So this is the textbook. for the course, and I just hold this up because it ruined 6 years of my wife's life when I was writing it, because you had to get the new chapter done on Friday prior to treating it in lecture, and the ink was just drying when I posted it. Now, Randy Goldsmith is teaching this course at Wisconsin, coming after Fleming Krim, who I gave a talk at Wisconsin about this, and he said, I've got to teach the course. Well, it turns out that Fleming got incredible flack from his students because there were typos. And as many of you know, typos occur in what you write while you sleep. They enter a hard drive. You didn't put them there, but Randy and Fleming and my students, so we've now cleaned it out so there are no more typos. Yeah, right. But my students were very forgiving because they knew exactly what was going on. So they said, "Oh, yeah, we know these chapters are unfolding as we speak," and so they were very gentle to me, but not not to Fleming and not to Randy. All right. Okay. So the textbook then starts out, and it starts out with a framework. This is 8 to 10 pages that describe why the core ideas in that chapter are so important in the larger context. Then the core of the chapter deals with these subjects, and then the third part are case studies that link these core ideas into the larger context. And these case studies are immensely enjoyable because they're changing all the time. So we have to rewrite them about every 12 months because these numbers are changing so quickly. Okay. The next piece of this course are called the 50 questions. And these are the 50 questions anybody graduating from a university with a straight face ought to know how to calculate. They're the back of an envelope calculations. And so they're really Fermi calculations. And they put great emphasis on knowing orders of magnitude and finding out ways of creatively calculating something without getting overly complex. And so they're also a big part of this. And so coming back to these 50 questions, one of them is, what's the ratio of power received from the sun to power consumed by the human endeavor? Is it 10 to 1, 100 to 1, 1,000 to 1, 10,000 to 1, 100,000 to 1? They can do this on the back of an envelope with a Stefan Boltzmann constant. Very, very simple relationship. They can calculate that out. It's 10,000 to 1. How do you calculate global energy demand? Well, of course, you can go around and interrogate 7 billion people and ask them how much energy they use, or you can come up with creative things like the product of population, measures of standard of living, per capita income in particular, and the amount of energy required per dollar of GDP, and you can calculate this very accurately, but it demonstrates that it's not population that's driving energy demand. It's actually increase in standard of living. As people move from the rural to the urban, they go from 200 watts per person to 2,000 watts. Now, the United States, every one of us goes through 10,400 watts. That's steady state energy consumption or power. Western Europe is half of that. But how do you calculate the increase in global energy demand? And then how many 600 megawatt power plants are required in the next 30 to 40 years to meet that? Is it one a month? Is it one a week? Is it one a day? Well, it turns out it's 2 a day. That's the scope of the problem. Now, when we look at the flow of energy through the economic structure of the United States, why is 65 to 70% of this wasted? And the Lawrence Livermore graphs are famous for this. And of course, once they understand thermodynamics, they understand the Carnot cycle, they understand that heat engines are generally about 15% efficient for converting chemical energy. It's very clear why 70% is wasted. Okay, what fraction of petroleum imports from the Western Hemisphere? It's now down well into the single figures. How do we calculate energy to propel a gasoline automobile? And what about what does this mean for the United States for cost? So we can quickly do that calculation, but this is the interesting one. If we all switch to an electric car tomorrow, how much would we save as a nation? So we currently spend about $480 billion on gasoline. If we all drove an electric car, we'd spend about $75 billion for electricity, and that would be a net change of $400 billion. Now that would involve an increase of about 20% on the grid load, but that's all. Next part of this course is News of the Week, and of course, a lot of them have a background to look at News of the Week. For example, if you look at the volume of ice in the floating ice in the Arctic, that was about 17,000 cubic kilometers in 1979 when we first started to get microwave data on this. And we're now down to about 3. But look at the highly negative first and second derivative of this. The profound feedbacks are driving this down with a very strong negative second derivative. And this is a result of the feedbacks that are intrinsic to the Arctic. Now, I just printed this out yesterday. This is from the University of Washington Applied Physics Lab. This is tracking this ice volume downward. And this, you can see the second derivative, but there'll be no more permanent ice left in the Arctic by probably 2022, somewhere on that range. And this isn't a model. This is just straight observations. And of course, the students in the class can do a calculation on received energy, energy going into the climate structure, so they can compare the circulating infrared radiation to the amount of energy required to melt Arctic ice at this rate. And when that calculation is done, there's a 50,000 to 1 ratio between the circulating infrared radiation between the Earth's surface and the atmosphere compared to the amount of energy required to melt ice at this rate. So ice is extremely delicate. It's a tiny heat of fusion for water, but it dominates the overall global climate structure, so it's extremely important. It's also fair to say that, you know, if humans could see in the infrared, they wouldn't vote the way they do. Next thing, Arctic ice, record low levels, so we keep track of this. And of course, it's Greenland that's sitting out here, a vestige of the last ice age, that is the next profoundly important problem, because in the 1950s, we have data from nuclear submarines, and the entire Arctic basin was locked down with an ice depth of 3.5 meters. Now, the small fraction that's left is only about 1.5 meters deep, and that accentuates that negative second derivative because solar radiation going in enters the upper 3 meters of the ocean. It's exactly where the vestige of this ice is sitting. But it was that block of ice that protected Greenland for so long because it extends to rather low latitudes. It has 7 meters of sea level rise in its ice volume. But it's now, we know from the paleo record, very unstable. So Greenland has this rapidly acquiring water on the surface. That's the red here shown. If I showed you 2012, the entire surface of Greenland would be water, but it pours down through these fissures in the ice, and it breaks the bond between the ice and the bedrock, which means that Greenland isn't going to melt, it's going to collapse. And so there are the data through 2012. Now, when we look at what this means, this 7 meters of potential sea level rise, this is central Cambridge. So this is the Charles River. This is where Harvard is building a huge new engineering structure. And it's surprisingly, they're coming up with a problem with the alums who happen to read. And they're asking them to contribute $100 million to something that'll be underwater in a quarter of the lifetime of the university. Now, the Harvard students also know that MIT will go under before Harvard does. So then the feedbacks go through this entire climate structure, and they know exactly how to calculate these feedbacks. I don't have time to go into them, but There are the Arctic-centered ones. There's the Greenland glacial loss, the Tibetan glacial loss, which is a water supply. That's 70% of the water to China, 90% to India. But the melting of clathrates turns out to be an extremely important part. So Michael Faraday's clathrates, applied to methane here, is an entirely entropic process. Nature abhors a vacuum, and anaerobic decomposition of organic material pumps methane into these structures, and there's 3 times as much chemical energy tied up in these clathrates than there is in all known reservoirs of natural gas, coal, and petroleum. And if you plot CO2 emission on the ordinate here in gigatons per year against the year, the amount released in fossil fuel burning exceeds the upper limit of every single IPCC model released, but just 0.5% of the labile carbon in the upper 3 meters of just northern Alaska and Siberia, just 0.5% release rate equals all fossil fuel burning. So these feedbacks are intrinsic to the chemical structure of what we have. Now, news of the week goes into the 2017 was particularly interesting in the United States because there's $350 billion worth of damage from storms in the Midwest over the Great Plains, the hurricanes, and the wildfires in the West are taking a massive toll. We discovered by accident, flying high-altitude aircraft, that these storms over the Great Plains of the United States are unlike anywhere else in the world, in that their intensity is such that water vapor is injected deep into the stratosphere, and that triggers exactly the same chemistry that takes ozone out over the polar regions, except this is over the central United States in the summer, only over the Great Plains. And of course, humans are extremely sensitive to UV. This is the number of new skin cancer cases in the United States against the percentage reduction in ozone column. 1% reduction in ozone column, an additional 100,000 cases on top of the 3.5 million that already are in place in the United States. So as you force the climate, you see these couplings that emerge that no one would ever have guessed. But by increasingly forcing them, these connections are made. Then the financial, this news, of course, comes out all the time. S&P is downgrading any of these municipal bonds because if it's going to be underwater in 25 years, it's not a good investment. Mark Carney of the Bank of England has been constantly warning about this, and then Moody's cites these climate risks and the downgrades associated with it. These lawsuits, of course, California is the hero here. In fact, California is going to go down in history as the guiding light for the United States in all of these aspects, and of course these lawsuits are taking place. I think just 2 days ago, New York is now suing ExxonMobil for misleading comments. The insurance industry is being profoundly changed. This is a talk that was given at Harvard by Liu Zhangya, who is leading the idea of building an international power grid. And so he's describing how China is moving, first of all, to build their own grid, then they're moving into Africa, because most of the population increase that will be occurring in the next 40 years is in Africa. It has 1.2 billion people now, projected to go to 3.8 billion. That's where the population increase is occurring, and that's where the standard of living increase is going to occur. And so China is extremely astute on looking at these. For every dollar the US puts into renewables, China puts in 3. Solar panels are a perfect example. So the dynamic that occurs week in, week out, this only takes about 10 minutes to click through news of the week. But when you watch it week in, week out, the dynamic that unfolds during the course is a remarkable message. The jet stream, we're all now highly aware of the large amplitude in the jet stream, which is caused by a decrease in the temperature gradient between the equator and the polar regions. As you soften that temperature difference, it allows the discipline that is generally applied to that jet stream to sag, and you get much larger amplitude variations, and they tend to stay that way for 3 to 4 weeks. That's what's driving this huge variance in weather. And the temperatures are running 45 degrees above normal over the Arctic regions. This is driving the wintertime melting, but it's all thermodynamics and it's all dynamics. And so just to summarize, one of the things that I conclude is that this idea of slowly backing off on CO2 and methane release, given the irreversibility of these climate structures, is simply pathetic. We need to terminate CO2 and methane emission immediately. We have to actively extract CO2 from the atmosphere, because the paleo record clearly shows that you don't have a stable situation until you're well below 300 parts per million of CO2. Well, we're at 400 parts per million of CO2, but you have to add methane, N2O, and CFCs. We're actually effectively at 500 parts per million. And then in order to reform these ice structures, because the question is, how do you take heat out of the Arctic to reform these ice structures? You can only do it by rejecting 3 to 4% of the incoming solar radiation. Okay, so I'm just going to end here. My wife and I own an electric car, as you can probably guess. So I have the police block off this circle in front of the econ department, and I have students in PS11 drive an electric car. This is very exciting, because I usually, about 180 out of the 250 have driven this electric car by the end of the term. And usually I get 10 to 15 students who have never driven a car before. That proves to be extremely exciting. But the message is one of show, don't tell, because once you drive an electric car, you realize that they're a vastly better device than any internal combustion car ever thought to be. And when they experience this, it's the old argument they're going to tell their parents, you need to buy an electric car. And of course, they will never buy an internal combustion car. Okay, so just to finish up, the point comes back to this increasing infusion of the chemical sciences into every aspect of society, which brings with it the involvement in almost everything we think about. So the physical sciences have a remarkable opportunity, but they also have a remarkable responsibility. So that's it. Thank you.
Does anyone have any questions for Dr. Anderson?
Well, that's not a very positive way of stating it, Jerry.
I apologize, Jeff.
All right, I have a question over here.
Yes.
So this is amazing. And as someone who does science education and curriculum stuff, I think this is remarkable. But as you mentioned, a whole chunk of this needs to be rewritten every year. So if we're thinking about making the education sustainable to make the world sustainable, who should be doing that, and how should we be supporting that, and how do you make a curriculum like this sustainable?
Okay, well, that's a very good question. When Harvard X is the Harvard part of edX, and that was the union between Harvard and MIT to build massive online courses that are free to students. So they asked me 8 months ago to build this course on Harvard X. So it's called PS11X. And in close competition with how foolish I was to decide to write a textbook for this course, I said, yes, that's consumed a massive amount of time because it's all shot in a studio, facing the camera. But all of the case studies are intrinsic to that Harvard X program. And so I'm rewriting them all the time. And the news of the week is a great help because I just go in and I keep track of everything that's changing. I update that. So it turns out it's not difficult to update the case studies that way because, first of all, it's so interesting to watch it. And if I look at something I wrote 2.5 years ago, I just say, my God, I can't believe how things have changed in just 2.5 years. It's just amazing. So it's very exciting to do this. So I don't find that that's an onerous process, but I can see why it would be. You mean since I'm so old, this is going to die soon? No, I'm just kidding. Yeah, no, yeah. What? So, actually, pose that question again. The last question you posed about sea level. What you said? You posed a very good question.
Oh, just if it rises to the point that this is irrelevant.
Yeah, you mean when it rises? Yeah. Because one of the things, the physics of the breakup of these glacial structures in Greenland and in the West Antarctic is fascinating. And one of the things I wanted to talk about here was the fact that we're just a month from launching something we've been working on for 3 decades, which is a solar-powered stratospheric aircraft that can fly for 12 months to 90,000 feet. And it can make radar, ice-penetrating radar measurements to map out exactly what's happening to these systems and actually create a trusted and believable forecast of sea level rise, because as you know, those forecasts are going up very quickly every year. I mean, if you take the second derivative of the projected or predicted sea level rise numbers, it's strongly positive. So I think my feeling is that the best thing that can happen, which will happen, is that these case studies will be rewritten by people across the country, because you know, you learn something and there are probably 5 times as many extremely interesting case studies than what I have in this textbook. And boy, you start writing these case studies and you learn so much. I mean, I've changed my mind about biofuels. Half the case studies I've written, after I finish them with the quantitative analysis, I've changed my mind fundamentally about these questions. So I think it's self-perpetuating, I hope. Yeah. Yes?
I really appreciated your talk. I wanted to push back a little bit on something you said in the very beginning, and that's that we're preparing upper division students and graduate students really well already. And that, I mean, I agree we need to focus on younger students as well.
Yeah.
But I guess my sort of perspective is that graduate education in particular is not doing great service to the types of people we're preparing and the types of jobs that they're taking. We're preparing them to maybe be an academic, maybe, but most of them are not going to go into that career.
Yeah.
So I was just curious
Okay,
about your
this
perspective.
is a really important point. I thought I would start out by saying something positive. That was part of my strategy. But I think it's also fair to say that the research endeavor is driving science and technology profoundly into the fabric of modern society. That was a point I was making. But you're absolutely right, and thank you for bringing that up, because in some ways this is a self-perpetuating process where, you know, I went through freshman physics, freshman chemistry, so you too have to, you know, and yet, I mean, I can't tell you how much fun it is to teach this course. I mean, I just, you know, I just, of course the students help too. I mean, they're really electric, but you're absolutely right. We've got to change the whole social concept around how important teaching is in infusing it. And of course, President Decatur made this point beautifully this morning. But thank you for pointing that out.
Well, as you know, people are slow to change. And so I wondered if you'd be willing to say a few words about something called geoengineering. First, telling people what that means and what do you think that the promise and pitfalls of that are.
Okay, well, thank you, Dick. So geoengineering takes 2 forms. One of them is called solar radiation management, and that is the insertion of aerosols into the stratosphere to reflect a certain amount of sunlight back, because that's the only way, for example, you can extract heat from the polar regions and reform the ice structures. It's just the first law of thermodynamics, basically. The other is carbon capture and sequestration. And so, of course, I'm profoundly in favor of extracting CO2 from the atmosphere, because as I pointed out before, until we get back to well below 300 parts per million, we don't have a stable climate structure because of the loss of the delicate cryosystems, particularly in the northern hemisphere. Now, the cost of doing that is about $100 a ton of carbon, and but the cost is starting to come down. There's no question that we're going to have to apply that at massive scale. Then we come to the more sensitive part of your question, which is solar radiation management. And having studied ozone for the past, well, since I took your course, which is about 100 years ago. That's not funny. I got okay, Dick, we're in this together. Ozone is probably the most delicate aspect of human habitability on the planet. If you took all the ozone in the stratosphere and compressed it to the floor of this room, it would be 1/8 of an inch thick. And yet it's the only thing that protects DNA against breaking the base pair across the double helix by ultraviolet radiation. We've heard a little bit about that already. So I'm extremely sensitive to anything that you put into the stratosphere that would damage the ozone layer, because if we do that, there's no point. We're much more sensitive to. But I'm also convinced that we have to do this, but we have to do it chemically so that we do not affect the ozone concentration. And I think there's real hope for that. Frank Koich in the chemistry department at Harvard is working on this, and we're going to test it out by actually inserting very small amounts of this and then sampling it with a solar-powered stratospheric aircraft that can watch the kinetics of the subsequent reactions. And people recoil in horror over geoengineering, but then I say, well, we're geoengineering the planet, all right. We're just doing it mindlessly. We don't understand what we're doing, how we're doing it, or the quantitative aspects of it. So we're already geoengineering. So.
Okay. I started teaching, I'm over here. 20 years ago, I started teaching general chemistry, and it's one of my favorite things to do. And in the earlier part of my career, I went to a lot of teaching workshops. And some of the things that you were saying at the beginning of the talk are echoes from those presentations about inquiry-based case studies, top-down. And at that time, the book that they were really promoting was this American Chemical Society, Chemistry in Context.
Yeah.
And I've taught out of that book a few times over my career. So I'm kind of wondering, do you think the reason why those approaches haven't gained greater momentum across science education, is it mostly because professors have a hard time teaching in a way they didn't learn themselves? Like, what do you think has been, because it's not, based on this presentation, it sounds like that approach is still not very common within science education.
Well, it's not very common at all. I looked at that work, and what struck me, and it was actually before I started pursuing this with a vengeance, what struck me was that, they take something like the chemistry of an airbag, and they'd use that. That's not going to drive freshmen to a sense of profound impact on the future of their life, their family, and how quickly it's happening. So the context has to be far deeper than that material suggested. That's what struck me about the failure of that. Even though, of course, in spirit, I think it was the right idea, but also it was very clear to me in the beginning that this course had to be a lot more rigorous than a standard freshman chemistry course, because the worst thing would be, oh yeah, well, this is chemistry for poets. Well, I'll tell you, I'm going to leave this up here. People can look at it. It's not chemistry for poets. I mean, it uses the Hamiltonian in quantum mechanics. The Carnot cycle. You have to fundamentally understand the Carnot cycle to understand heat and work. And boy, the ramifications of that and how it plays into heat pumps, and how beautifully this entire structure can electrify. The only thing you need liquid fuels for are aircraft, but biofuels can more than handle that. So the gorgeous world we would have if it was electrified is just a shocking part of the message, I think. So.
Hi, I
Yes,
am a
hi.
science educator.
Uh-huh.
Can you hear me? I teach chemistry at the high school level to elite students in New York City. And I've thought about what is taught at high schools a lot. And I'm actually not a big fan of AP chemistry, as it is
Good.
completely uncontextualized. And unfortunately, over in the United States, when a student says, I want to take advanced chemistry, that is where they go.
Yes. Oh.
So as a solution, well, last year, a few years ago at my school, we have a new principal who is very open to really making the curriculum much more contextualized and giving teachers an opportunity to do so. So I had developed a class last year in which we started looking at problems, what the scientific basis for those problems is, and what particular solutions there are. One of the things we talked about was electric cars. Just one thing to point out that was very interesting, before I even started the unit, I asked the students, please make a list of all the electric cars you know of. Many of them did not even know the name of an electric car, which really surprised me. Over the course of the unit, we talked about lithium battery design and what you put in the cathodes and the anodes. And we also looked at news articles, a lot in the Wall Street Journal. And part of when you build lithium batteries, you need cobalt as part of that battery.
Yep.
And one thing that was in the news last year was cobalt mining in the Congo.
Right.
Yes. And I was wondering if in your course you talked about that. And also one thing that I was thinking about is if electric cars do take off more than they are used now, then we actually might have might not have enough minerals to be able to make all the batteries we need to make. Did that come up at all in your course?
Oh, yes. Oh, thank you very much for this question, because you hit the nail on the head with this AP thing, and it's a kissing cousin of the SAT exam. And it takes me 2/3 of a semester to unteach that garbage. And the problem is that they come in thinking science is a reptilian identification of an equation into which you stuff a number to get an answer. And it's dry, it's dead, it's lifeless, and it's pathetic that it's endemic across this country, and it's a real problem. So your question about electric cars is very interesting, because whenever I give a talk, how many people here have driven an electric car? How many people own one? Good for you. So I asked my class of 250, and a lower fraction of them actually raised their hand that they have driven an electric car. Not that they own it, but they've driven it. So, 5, 6, 7 out of 250 have driven an electric car. So that's why I say, well, we're going to drive an electric car, and by the end of the term, there are 180 hands that would go up. So this is a really crucial point, and the electric car is so much better as a device. Then you come to cobalt, lithium, and the Congo is a perfect example, because the Congo has problems that are unbelievable socially, in governance and everything else. And the technology that goes into batteries that have, let's say, 400 kilowatt hours per kilogram of capability, that is a massive research frontier, and a lot of that research is actually pointing toward more common elements. So lithium-ion batteries are running about 200 kilowatt hours per kilogram now. They're a very, very important starting point, because, of course, the Tesla Model S will go 300 miles on a charge, and at 440 volts DC, you can charge it in 20 minutes. So it's getting the capability out there, but the chemistry that goes into battery technology is just fascinating. I mean, electrochemistry, many of you can vouch for this. 8, 10 years ago, you'd get to the electrochemistry section and go, oh God, it's a lead acid battery again. I'm going to get through this as fast as I can. Electrochemistry now, so to speak, lights up the entire course because it's so intriguing chemically and has such a massive impact on society. So yeah, news of the week of cobalt in the Congo, it definitely makes news of the week. Yeah.
Thank you. Jim?
Yes, Mark.
I don't know how this works, but
You just talk into it.
can you hear me?
Yes. Uh-huh.
When you talk, it seems that some extraction of CO2 from the atmosphere is inevitable. Could you talk a little bit about where you might put it?
Yes. So we get back to thermodynamics. What are you smiling about? Yeah, okay. Mark and I have an infinite amount of fun over the years, so you know. So thermodynamics is a key part of this problem because you can actually insert it under the ocean bottom at depths more than 2,000 meters, and it's thermodynamically stable because of the pressure and the temperature. But it also reacts to form carbonates, and so there are large areas where you can inject it in and it irreversibly is converted to a stable material. In fact, the reason we had so little CO2 in the atmosphere was that carbonate silicate reactions of the acidity intrinsic to rain that struck rocks liberated the silicates and sucked all of that carbon dioxide out of the atmosphere from 1,000 ppm down to 250, and that's what formed, of course, all the limestone, sandstone, and so on the bottom of the ocean. So my first reaction was exactly yours. I said, you know, you're not going to be able to bury all of that somewhere. But I've changed my mind, and the case study helped convince me that, in fact, it's highly viable, and it has the Earth has a virtual infinite capacity to take CO2. But it's a really good question because it's one.
More under the water than injected into the ground?
Well, you could put more under the ocean, much more than you could, but there's adequate reservoirs in the chemical systems just below the surface that you could put all the CO2 you want into those. Yeah, but it's a really good, important question.
So, sorry. Okay. A really compelling vision. I'm really excited about this. I wonder if you could say a few words about the students that don't do well in a course like this. And then I guess the other side of that question might be, it's such a compelling vision. You know, have you thought about ways that courses like this could be offered to more advanced students in the natural sciences, or, you know, students in the public policy school, for instance, you know, beginning master's students?
Well, let me start with the last question. Teaching this, I have a course at the junior-senior level. It's called Physics and Chemistry in the global context, and I get a lot of students from the Kennedy School in that course. But it turns out that the time commitment to teach this, develop the text, and now do this on Harvard X is such that I'm investing virtually all of my efforts into this particular course. And so the first part of your question was?
Who does not do well?
Oh, okay. This is another interesting thing. A lot of the students do terribly on the first exam. And when I've watched these students over time, and I've done this for 6-7 years now, lots of times those students end up being the best students in the class. And a lot of it, of course, is you're tracking their background in chemistry and their maturity level and all sorts of things that can evolve very quickly over a semester. And so I write exams that I think would have a median of 81, 82 typically. And typically the median score is high 80s to low 90s. And there's no way I could get that kind of grade on one of these exams. I mean, the idea that you could understand it all. Now, I don't put time pressure on them, but one little mistake, so the other important aspect is that, anybody who wants to take a look at this, that we do this in one semester. And Harvard X took a look at it and said, you're crazy, this is 2 semesters, and so it's a 2-semester course on Harvard X, but the only reason we can get away with it is that not only do we have good students who have opted into the harder course, but they're really juiced about it, and we have 1 snow cancellation, and it causes real problems for this course. I mean, the time is the tyranny in this thing, but the performance of students, I don't think this is ever going to be an issue that's unique to my university. Every university, students from any university can handle this just fine. I have no question about that.
Yeah, it's here. Yeah, Jim, this is really amazing. I think if that can be sustainable, I think it will make a huge impact. And so I think go back to the earliest questions, follow up on that for the sustainability. How easy is it for other people to update those case studies? And if it's not too difficult, then is it possible, or what would you think about having a Wikipedia page for each case study? That having someone constantly update that case study, then hopefully that can be sustainable and
that's
continue.
a really good idea. Yeah, there's no reason why you couldn't. It would be so much fun to watch what happened on that site. It's a very good suggestion. Yeah.
Yeah, so Mike, when you're talking about a curriculum like this, there's always a question about adaptability and broad scalability, right? The wiki solution would help that, right? It would make each individual instructor feel like they weren't on the hook year after year for adjusting their course material, because let's just say I know some people who are still using an edition of their textbook that's 10 years old because they don't want to change the problem set numbers on their syllabus, right? So one of the big barriers to adoption is that some folks just don't want to do this, right? And so you've removed some of the barrier, you've proven it can be done, and a wiki-type solution will allow it to be sustainable so it's not just on your shoulders or other people's shoulders. But my question is really this: it's about preparedness into and out of the course. Math readiness is a major concern for general chemistry curricula that I don't think we've really addressed effectively, in part because we don't have a ton of control over it. What math readiness do you expect for incoming students? And then just to follow up on the output side, what do they do next for students who take a science course after this? What is their next science course? And do those instructors of those science courses feel these students are adequately prepared for those next course?
Okay, let me preface what I say by revealing my prejudice, and that is that at my university, when you're going into engineering, the sciences, earth, planetary science, whatever, you have to take 2 intro physics courses, 2 intro chemistry courses, and 2 math courses. And when I look at the way those courses are designed, and this is one of the reasons I called this Physical Sciences 11, not Chemistry 11, was that let's take Michael Faraday, who is the father of electromagnetic induction and of electrochemistry. What happens to everything he did? It's chopped right down the middle, and the physics department teaches electromagnetic induction, the chemistry department teaches electrochemistry. If you fuse chemistry and physics together, and then you use these physical models to teach mathematics, you could teach far more effectively in 4 semesters than it currently is done in 6, because these students walk in, they take isolated mathematics, isolated physics, and isolated chemistry. And I just think it's terrible. I mean, when I need physics in this course, I use it. I don't blush or make, you're calculating the torque from an electric motor for an electric car and the current and everything. Electromagnetic induction can be taught very, very quickly and effectively. And I do that all the time. So the mathematics in here I teach through physical models. I don't put mathematics up and then not use it in a physically connected way. And of course, the integral of dx over x is probably the most important integral in all of science for flexibility, and it just goes through every single aspect of this. Gibbs free energy Gibbs free energy is introduced right at the beginning of thermodynamics, and I use it all the way through equilibria, acid base, electrochemistry. Everything's on a Gibbs free energy surface. So a lot of the mathematics and so on is I teach it repeatedly, and I teach it always with a physical model. So, okay, and then the last part of your question was, well, what do they see next? Well, it depends on what they're going into, but they would, for example, see organic chemistry. And of course, for many years there was idea, well, let's just skip freshman chemistry and go right into organic chemistry. Well, that's a reflection not so much on organic chemistry, but on how pathetic freshman chemistry was. If it's high school chemistry, you know, on steroids, if it's AP chemistry all over again, well, God, I hope you skip it. But freshman chemistry is a foundation that provides massive opportunity if it's done correctly. Now, inorganic chemistry is the other course that they would take coming out of this, but in all cases, they have a profound grasp of molecular orbital theory, valence bond theory. They aren't afraid of the Hamiltonian. They're afraid of it the first time I put it up, you know, all those partial derivatives and so on. But when they see that you don't have to solve that equation for the single electron atom each time, but more than that, once you understand what those orbitals are telling you, you can apply that to multi-electron systems, to molecular systems, and everything else. So this is a very, very strong preparation for both organic and inorganic chemistry.
So I'm a theoretical and computational chemistry, and I've been thinking a lot about how to bring computational chemistry to the general education early on, and also how to make them start doing research. I think that the examples of questions you posed are wonderful examples to actually integrate computation theory and also some research ideas together. So my question is, can you share with us about insights or the thought process that you came up with those questions? I mean, the question, I mean, what I think it's important for chemistry education to be interesting. So but also it's important for us to provide the right skill set so that they can be prepared for their future. And I always find it's difficult to kind of come up with a balance between being interesting and also being useful. And with your experience, I would like to see, I mean, whether those questions are based on your teaching experience, or do you have any kind of the thought process or the design process for those important questions?
Well, there are many facets to answering that. Those are very good questions. Let me look at the numerical analysis part first. One of the things that I've toyed with very seriously is having them solve problems with numerical analysis. And if I had 2 semesters in this course, I would definitely do that. I mean, it's extremely important. Now, part of my prejudice in going into this was that I worked doing measurements over the Antarctic that established why we have an Antarctic ozone hole. That drew me into the ozone wars, which, you know, was hand-to-hand combat with DuPont for many years and a lot of testifying in front of the Senate. So when I saw unequivocal science collide with public policy, that was kind of a background. But you know, that was 25 years ago when all that started. Our work now primarily is the collision between chemistry and climate, but it's just dripping with exciting questions and problems. You know, that made it so interesting to do this course and vastly easier to do it. But you know, this Harvard X course that we're working on now, one of the big advantages there is that I think I have them convinced to do a digital platform. So this textbook is only $20 off of a digital platform. So it's going to be uniformly available to anybody for nothing, virtually. I mean, now you pay, what, $250 for freshman text? It's $50, you know, I just go, oh my God. Because if I didn't have these exciting questions to drive this course, I wouldn't be teaching freshman chemistry. I mean, but as I said before, I can't wait for every lecture because it's so exciting and the kids are so interactive. And I use, I only lecture for 10 minutes before I pose a question to them. It's a clicker thing, because Dave Pritchard at MIT did this research showing that a human only focuses for 10 minutes before they start to, but you pose a question to the class and the adrenaline level jumps up, and then I play it out on a computer that comes up on the screen. I can see whether they understood what I said, and if they didn't, why they didn't. But it builds in this interaction, and you have groups of students in this large, they form, I call them the juries, you know, and they're asking questions all the time. But a lot of it is because the context is so interesting for them. So.
If there's no more questions, maybe a round of applause for Jim Anderson.